experiment shows how changing the spring constant, the mass of the bob, and the amplitude of the weight being pulled down changes the period of the bob. To first demonstrate how the period changes, we used 3 springs with 1 mass. At first we used the 0.02 kilogram weight. The largest spring we used was 0.073 meters unstretched. It had a spring constant of 1.88 newtons per meter. It took 8.72 seconds to do 10 bobs, so its period was 0.872 seconds. The medium-sized spring was 0.052 meters unstretched. It has a spring constant of 2.33 newtons per meter. It took 7.20 seconds to do 10 bobs, so its period was 0.72 seconds. The smallest size spring we used was 0.027 meters unstretched. It had a spring constant of 3.34 newtons per meter. It took about 4.78 seconds for it to do a cycle of 10 bobs, so its period was 0.478 seconds. When looking at this chart, you can see the tighter the spring is, the shorter the period. Next, we used 3 different masses with a medium-sized spring of 0.052 meters to show how using different masses can change the length of your period. When we put the 0.01 kilogram weight on the medium spring, it took 4.5 seconds to do 10 bobs, giving it a period of 0.45 seconds. When we put the 0.015 kilogram weight on the medium spring, it took 6.08 seconds to do 10 bobs, giving it a period of 0.608 seconds. When we put the 0.020 kilogram weight on the medium spring, it took 7.25 seconds to do 10 bobs, giving it a period of 0.725 seconds. When looking at the chart, you can see as the weight increases, the length of the period also increases. Next, we changed the amplitude of the weight on the spring. In other words, we changed how far we pulled down the weight before letting go to measure the 10 bobs. For each trial, we used the medium-length spring with a 0.020 kilogram weight on the end. Each time we pulled down the bob, we increased it by a length of 2 centimeters. The bob started at about a length of 25.8 centimeters. We pulled the bob down 2 centimeters. It took 6.6 seconds to go a cycle of 10 bobs, giving it a period of 0.66 seconds. Next, we pulled the bob down 4 centimeters. It took 6.8 seconds to go a cycle of 10 bobs, giving it a period of 0.68 seconds. Next, we pulled it down 8 centimeters. It took 6.92 seconds to do a cycle of 10 bobs, giving it a period of 0.692 seconds. From looking at this chart, you can tell that as the amplitude increases, the period also increases. In conclusion, we found out the larger the mass, the longer the period, the tighter the spring is, the shorter the period, and the bigger the amplitude, the longer the period. In the case of a mass spring system, like the one just demonstrated, the relationship between force and displacement is known as Hooke's law. This equation describes the relationship between force and displacement mathematically. The negative in the equation signifies that the direction of the spring force is always opposite the direction of the mass's displacement. The K stands for the spring constant. The value of the spring constant is the measure of the stiffness in the spring. The greater value of K means a stiffer spring because a greater force is needed to stretch or compress that spring. We made 3 charts, one for each different size spring, to sort out our data and find each spring constant separately. First, we need to find the force of gravity using the equation F equals ma for each different weight. Next, we measure the spring before the weight is applied, then the length of the spring after the weight is applied. We want to find the displacement of the spring, so take the stretched length and subtract the unstretched length. That will give you your displacement. In our experiment, we decided to make the displacement negative because we kept our force positive. Next, you want to find the spring constant K. Take your number you got for the force and divide by the displacement. Use the equation F equals negative kx, but manipulate it so it becomes K equals negative F over x. The reason why the force becomes negative is because you want the K to be positive. So you multiply each side by a -1, giving you a positive K and a negative F. You can use the same method to find each spring constant for each different size weight. As you find the spring constant for each different size weight on the 0.073 spring, we discovered that the spring constants were not very similar. The reason for that was because we reached the limit of the string's stretching ability. Because the spring constants were so far off, we calculated the spring's average spring constant. We added up all three forces divided by 3, add all three displacements divided by 3. We then put those numbers into the k equals negative F divided by x equation and got an average of 2.40 newtons per meter. Next, we used the medium-sized spring with all three different size weights. Using the same method you used on the first spring, you can find the spring constant of the spring with each of these three weights. The spring constant was very similar on each one of the weights. We found the average spring constant to be 2.35 newtons per meter. Next, we used the smallest size spring with all three different size weights. After finding the separate spring constants of the spring with three different weights, we got the average spring constant. It was 3.37 newtons per meter. A greater value of K means a stiffer spring because a greater force is needed to stretch or compress that spring. The last spring that we tested, which was the smallest one, had the greatest K, which meant that it was the stiffest one.
These demonstrations show the relationships between period with mass, amplitude, and length. To find the period, you divide the time by the number of bobs. This demonstration is a relationship between period and mass. The mass doesn't affect the pendulum's period. This demonstration is a relationship between period and amplitude. This also doesn't affect the pendulum's period.
definition of a transverse wave is a wave whose particles vibrate perpendicular to the direction of the wave motion. This is different than a longitudinal wave because the particles of a longitudinal wave vibrate parallel to the direction of the wave motion. In this experiment, our goal was to determine whether the amplitude affects the speed of the wave. We chose 3 different amplitudes and timed the waves. Each amplitude had the same time, so we concluded that amplitude does not affect speed. This is because wave speed only depends on the medium. In this experiment, our goal was to determine whether the tension of the spring affects the speed of the wave. We chose 3 different spring tensions with the same amplitudes, and as the spring tension increased, the time decreased. From this data, we concluded that tension does affect speed, and as tension increases, so does the speed. In this experiment, our goal was to determine if the amount of standing waves affects the speed of the wave. When we calculated the velocities of 1, 2, and 3 standing waves, we found that they were all very close. The slight variations could have been due to timing errors. Because there was no clear pattern, we can conclude the number of standing waves doesn't affect the speed of the wave. This demonstration was to show the difference between a free end and a fixed end. With a free end, if the wave motion begins on the right side, it will reflect back on the right side. With a fixed end, if the wave motion starts on the right side, it will reflect back on the left side. This demonstration shows the difference between constructive and destructive interference. With constructive interference, two displacements on the same side add up together to form a resultant wave, then continue moving on the same side of the equilibrium. With a destructive interference, displacements on opposite sides of the equilibrium subtract to form a resultant wave, then continue on the same side of the equilibrium, but one pulse is subtracted from the other.